Have you ever heard the phrase quantum computer and felt like your brain was trying to solve a Rubik's Cube blindfolded? You're not alone. It sounds incredibly futuristic and complex, but at its heart, a quantum computer is just a different way of doing calculations. While our everyday computers use simple bits, quantum computers tap into the bizarre rules of the quantum world to unlock mind-boggling new possibilities. Today, we're going to demystify what makes these incredible machines tick, piece by piece, so you can finally understand the hype. Let's dive in. Before we jump into the quantum realm, let's quickly remember how our current computers work. They speak in binary, a language of just two digits, zeros and ones. Each of these zeros or ones is called a bit. Think of a light switch, it's either on, 1, or OFF, 0. Your phone, laptop, and even that smart toaster operate by combining millions or billions of these simple bits, flipping switches on and off incredibly fast to process information, store data, and run all your apps. It's a very straightforward, definite system. Now, let's meet the qubit, the quantum equivalent of a classical bit. Qubits are the fundamental building blocks of quantum computers. Unlike a classical bit, which must be either a 0 or a 1, a qubit can be much more complex. It's not just a light switch, it's like a spinning coin. While it's spinning in the air, it's neither heads nor tails, it's a bit of both. Qubits leverage strange properties of quantum mechanics, like the spin of an electron or the polarization of a photon, to exist in multiple states simultaneously. The most mind-bending property of a qubit is superposition. This means a qubit can exist in a combination of both 0 and 1 at the same time. Instead of being just heads or tails, our spinning coin is simultaneously both until it lands. This isn't just rapidly switching between 0 and 1, it's genuinely existing as a probabilistic blend of both states. This ability is incredibly powerful because it allows a single qubit to store exponentially more information than a classical bit. Imagine the possibilities of processing multiple outcomes at once. Here's the catch with superposition: you can't just look at a qubit to see its combined state. The act of measuring a qubit forces it to collapse into a single, definite classical state, either a 0 or a 1. It's like catching that spinning coin. Once it's in your hand, it's definitively heads or tails. You only ever see one outcome, but the trick is that the quantum computer calculates using all possible outcomes simultaneously before that final measurement. The probability of measuring a 0 or a 1 is influenced by the calculations. Beyond superposition, there's entanglement, a phenomenon Einstein famously called spooky action at a distance. When two or more qubits become entangled, they become intrinsically linked. This means that the state of one entangled qubit instantly influences the state of the other, no matter how far apart they are. If you measure one entangled qubit and find it's a 0, you instantly know the state of its entangled partner, even if it's light years away. They are not communicating, their fates are simply intertwined. Why is entanglement so important? Imagine two entangled qubits. They can represent four possible combinations, 0, 0, 0, 1, 10, 11, simultaneously. With three entangled qubits, you get 8 combinations. This power grows exponentially. For every qubit you add, the number of possible states you can explore at once doubles. This incredible parallel processing capability is what gives quantum computers their potential to solve problems that are utterly impossible for even the most powerful classical supercomputers. It's a massive leap in computational power. The final major piece of the quantum puzzle is interference. This concept comes from wave physics. Think of waves in water. When two waves meet, they can either combine to make a bigger wave, constructive interference, or cancel each other out, destructive interference. Qubits, because they exist in superposition, also have wave-like properties, where the wave represents the probability of measuring a certain state. Quantum computers carefully manipulate these probability waves, amplifying the correct answers and canceling out the wrong ones. It's how they find the needle in the quantum haystack. So, how do we actually make these magical qubits? One leading approach uses trapped ions. Here, individual atoms are stripped of an electron, making them charged ions. These ions are then suspended in a vacuum using electromagnetic fields, forming a tiny chain. Precise lasers are then used to control the internal quantum states of these ions, defining their zeros and ones, creating superposition and entanglement. This method offers very high fidelity, meaning the qubits are quite stable, but it's challenging to scale up to many qubits. Another prominent method for creating qubits involves superconducting circuits. These are tiny electrical circuits, often made from metals like niobium or aluminum, that become superconductors when cooled to extremely low temperatures, just a fraction of a degree above absolute zero. At these temperatures, electrons can flow without resistance, creating quantum phenomena that can be manipulated to act as qubits. These circuits are highly scalable and can be manufactured using similar techniques to classical computer chips, but they require extreme refrigeration. Once we have our qubits, we need to manipulate them to perform calculations. This is done using highly precise quantum gates. For trapped ions, this involves focused laser pulses that can nudge an ion's quantum state from a 0 to a 1, or into superposition, or even entangle it with another ion. For superconducting qubits, scientists use microwave pulses, essentially tiny radio waves, to control the flow of current and induce quantum changes. These control mechanisms need to be incredibly accurate to avoid errors, which brings us to a major challenge. Just like classical computers use logic gates, like AND, or NOT, to perform operations on bits, quantum computers use quantum gates to manipulate qubits. These are operations that change the state of one or more qubits. For example, a Hadamard gate can take a qubit from a definite 0 or 1 state and put it into an equal superposition of both. A CNOT gate can entangle two qubits, where the state of one qubit determines the flip of another. By combining sequences of these quantum gates, we can build complex quantum algorithms. So, what can these incredibly complex machines actually do? Quantum computers are not meant to replace your laptop for browsing the internet or playing games. Instead, they excel at very specific, difficult problems that classical computers struggle with. This includes simulating complex molecules for drug discovery or new materials science, breaking modern encryption methods, and optimizing incredibly complex systems in finance or logistics. They can explore vast numbers of possibilities simultaneously, finding optimal solutions much faster. It's important to understand that quantum computers aren't here to replace classical computers entirely. Instead, they're more like specialized coprocessors. Classical computers are still king for tasks like email, video streaming, and word processing. Quantum computers will likely work in tandem with classical ones, handling the specific, computationally intensive quantum problems, and then feeding the results back to a classical system for interpretation and further action. Think of it as a powerful, specialized calculator for unique, complex challenges. One of the biggest hurdles in quantum computing is decoherence. Qubits are incredibly fragile. Their delicate quantum states, like superposition and entanglement, can easily be disrupted by even tiny interactions with their environment, things like stray electromagnetic fields, vibrations, or even minuscule temperature fluctuations. When decoherence occurs, the qubit loses its quantum properties and collapses into a classical state, destroying the ongoing calculation. Protecting qubits from decoherence is a monumental engineering challenge. To combat decoherence, especially in superconducting qubit systems, these quantum computers need to operate at incredibly low temperatures. We're talking colder than outer space. Dilution refrigerators are used to cool the qubits down to millikelvin temperatures, that's just a tiny fraction of a degree above absolute zero. This extreme cold minimizes atomic vibrations and thermal noise, helping qubits maintain their delicate quantum states for longer. Building and maintaining these sophisticated cryogenic systems is a huge part of the quantum computing engineering effort. Even with extreme isolation, qubits are still prone to errors. They can randomly flip their state or lose entanglement. Quantum error correction is essential for building useful quantum computers, but it's incredibly complex. Unlike classical error correction, where you can simply copy a bit to check for errors, you can't clone a quantum state without destroying it. Instead, error correction in quantum computing involves encoding one logical qubit across many physical qubits, creating redundancy to detect and correct errors without directly measuring the quantum information. This requires many more physical qubits than logical ones. Despite these challenges, the potential of quantum computing is immense. In the future, these machines could revolutionize drug discovery by accurately simulating molecular interactions, accelerate the development of AI, create new materials with incredible properties, and even optimize global logistics on an unprecedented scale. We're still in the early stages, sometimes called the noisy intermediate scale quantum or NISQ era, but the progress is rapid. Researchers and companies are pushing the boundaries, working towards fault-tolerant quantum computers that can truly unlock their full promise. It's crucial to manage expectations. Quantum computers are not going to make classical computers obsolete, at least not for a very long time, if ever. They are specialized tools for specific, incredibly hard problems. For the vast majority of computing tasks, your smartphone or laptop will remain far more efficient and practical. The exciting part is seeing humanity develop a completely new kind of machine, based on the fundamental laws of physics, to solve problems previously thought unsolvable. It's a journey into the unknown, and we're just at the beginning. And there you have it. From classical bits to quantum qubits, superposition, entanglement, and interference, you've taken a journey through the fundamental concepts of how a quantum computer works. It's a field brimming with complexity and potential, pushing the boundaries of what we thought possible with computation. We're witnessing the dawn of a new era, where the bizarre rules of the universe are being harnessed to solve humanity's greatest challenges. Keep exploring, keep learning, and who knows what quantum breakthroughs you might contribute to one day.